Hello, Tensor friends. I got a hard question here, which I'm not sure I can answer. What are surface Christoffel symbols for? So I went through these derivations when I was made the playlist on Gaussian curvature, and quite honestly, I never did understand what's the big deal here. It seems to me to be much ado about nothing. And let's look at it. I can gain some insight into it geometrically, but why it was stuck in there, I still don't know. Let's remind ourselves what the Christoffel symbol is. When we take the partial derivative of a vector with respect to a coordinate, we use the product rule, bada bing, bada bong. This guy here is defined as the Christoffel, the symbol. So we have the derivative of a vector is a vector, which has a basis vectors and components. Okay, so uh, if you change now the way it was done in the book I'm using, which is Pavel Grenfield's book, when he changes from the ambient space to the surface, the coordinates, he changes from Latin indices to the Greek indices. So let's go look at what we're talking about. Okay, we have a Cartesian space here, right? And this is called the ambient space. In this ambient space, I'm going to define a position vector. I'm going to put a point on the end of it, and I'm going to put a manifold. And we use the sphere because it's so much easier to use. And the sphere, now on the surface of the sphere, there's two coordinates. There's theta, which is this angle, and phi, which is this angle. Okay? So he's going to use everything that relates to what's going on this called the two sphere. He's going to have the Greek indices for what happens on the surface, and he's going to have the Latin indices for what is referenced to this ambient space. So the sphere is embedded in the ambient this space. Okay. Now on this the surface, we can define the e theta basis vector and the e phi basis vector, and they also obviously move around with everything else. But now the way this is explained, or the way I understand it, is that these guys exist in a tangent plane. Okay. So they're both in a tangent plane, and that tangent plane moves along, they move along with the tangent plane like that on the surface. Okay. So that's where we are so far. Okay. So now to get back where we were, so there is a vector, a surface vector, which has the surface basis vectors and surface components. Okay. So when we differentiate that the same way, but we're differentiating it with respect to a surface coordinate, we get the same stuff, and we wind up with this. Okay. Now, what is this guy? The derivative of a surface basis vector with respect to a surface coordinate. So let's do an actual example. So in our case, alpha beta is a theta and phi, right? So we can write out the way we normally would the change in e theta. So that's this guy with respect to phi. That's this guy. Gives us this Christoffel symbol with this summation index. So our free indexes are theta and phi. Bing, bing, bing. And our summation index, the first case is theta, the second case is phi. Okay, now many, many videos ago, we've solved this several times. The non-zero Christoffel symbols for the surface of a sphere are these three. All right, so do we have a theta, theta, phi? No, so this is 0. Do we have a theta, a phi, theta, phi? Yes, right there. Okay, so we're going to wind up with this. The cotangent of theta is equal times the phi basis vector is equal to this derivative. Okay, well, we know what the phi basis vector is. It's this. We've done that derivative also. Cotangent is just cosine the theta over sine theta. We distribute that and we wind up with this expression. So now we have a vector, okay? And that vector is going to be the change in E theta with respect to phi. So let's go look at that guy. Okay, we're back on our graph. I removed the sphere because it makes everything easier to see. So here's my tangent, the plane. Here's my two basis vectors. Now, if I cross these two basis vectors, it defines a normal. Okay, now this normal is sticking out into the ambient space, right? Sticking into the ambient space. These guys are in a tangent plane. Now, that the vector we just found, which was the derivative of E theta, let's get rid of the phi basis vector. So the derivative of this basis vector with respect to a surface coordinate of phi results in a vector that looks like this. Well, where is it? It's not there. Oh, look, it's out of the tangent plane. It's out of the tangent the plane. And so because it's out of the tangent the plane, that means that it has a projection on the tangent plane, on the surface, and it has a projection on the normal, right? So if I crossed d phi e theta, I would have had a normal sticking in this direction. So there is a component of this vector in the normal and a component on the surface. So that is the whole deal about what we're getting ready to look at. Okay, so the way this is explained, and I can understand it because we just saw it geometrically. It made more sense when I did that to me. It did anyway. Is we got the normal stuff that we expect to see, but because that vector is no longer in that plane, it also has a projection in the normal. So you have to add a normal component, right? And that normal component, now this is a vector also, so it needs a component to go with the normal, the vector. And because we have these two free indexes, they put a B here with those two free indexes, and this B alpha beta is called the curvature tensor, which by itself, later on in the playlist that I'm working on, that you're looking at, it did have uses. But in this case, if you go through the pain and anguish of isolating this from all the rest of this mess here, you wind up in finding the Christoffel, the symbols called the surface Christoffel, the symbols, and you get exactly the same answer as this. So just by using the metric tensor on the surface of a sphere, that's how we derive these, right? Using the metric tensor on the surface of a sphere, we got these three. Well, if you go through this concoction of isolating this and solving for it, now these are matrices, right? This is a pain in the butt. You get the same answer. So I'm afraid you're going to need a mathematician to answer that question. But maybe if you go to higher dimensions, what if you have a three-dimensional the surface instead of a two-dimensional surface? Do you need this to find that? I don't know. To me, it doesn't seem like it's necessary that this is the way we found it, and that's the same answer you get here. So I'm sorry I couldn't be more specific than that, but honestly, I don't think I understand it either. All right, see you later.